Now that we are familiar with the unit circle, let's begin to examine the graphs of sine and cosine. In this video, we will graph the relationship between the sine of the angle and the angle itself, and also the graph of cosine of the angle and the angle itself. For an excellent perspective of how to visualize these relationships, I highly recommend this YouTube animation, so check it out. We will begin generating the graph of sine of x using a fundamental elementary approach. That is, we're going to plot some points and connect the dots. So in example 2, our goal is to graph the basic sine function y equals sine of x. Now, let me make a comment here about the input and output of this function. The input to a sine function is an angle. There's no surprise there. The output to a sine function is a ratio. We learned in chapter 1 that sine represents the ratio y divided by r, and we have just refined that definition to sine of x equals y, or sine of the angle alpha equals y. So I want you to distinguish between the input and the output. On the x-axis, we're going to take the angle of the unit circle and stretch it out in linear form. And on the y-axis, we're going to represent the ratio or the output of this sine function. To begin generating the graph, we're going to choose some basic angles. That's what you see here in this first column. X equals 0, pi over 2, pi, 3 pi over 2, and 2 pi. You can see that we're using just the quadrantal angles here. Then in the second column, we're going to evaluate the ratio. So if we look at 0 radians and we evaluate sine of 0, we know we can pick up the y-coordinate there. The output is 0. If we rotate to pi over 2 radians and find sine of pi over 2, we can see the y-coordinate there is 0. Continuing our way around the unit circle, when we get to pi radians, sine of pi is 0. And at 3 pi over 2, sine of 3 pi over 2 is negative 1. And back to 2 pi, sine of 2 pi is also 0. So we have a list of ordered pairs here that we can use to begin constructing the graph of sine. These are what is known as the 5 key points. So let's go ahead and plot these values on our graph. The first ordered pair is the origin 0, 0. Now, to plot the second ordered pair, pi over 2, 1, I do need to label the scale on my y-axis. To make this really easy to read, I'm going to use 2 tick marks to represent 1 unit on the y-axis. This will make the graph big enough so that we can see the details. So here we can plot the point pi over 2, 1. Then the next ordered pair is pi 0, that's an x-intercept, 3 pi over 2, negative 1, and 2 pi 0, another x-intercept. So looking at these 5 key points, we can begin to conceptualize the pattern of the sine function. It graphs as a wave. This is what's known as a sinusoid or a sine wave. We have 3 x-intercepts, we have a maximum point and a minimum point. Now, the graph of sine continues beyond these points that we've constructed. This is just a representative snapshot of sine. But this pattern is actually going to repeat across the entire domain of the sine wave. So let's use the unit circle to generate a few more key points on this graph. If we rotate to negative pi over 2 radians and we find sine of negative pi over 2, we can see the value there is negative 1. So we have ordered pair negative pi over 2, negative 1 on the graph. If we rotate to negative pi radians, sine of negative pi is 0. So we have another ordered pair negative pi 0. Continuing around to negative 3 pi over 2, sine of negative 3 pi over 2 is 1. So we have ordered pair negative 3 pi over 2, 1. And then back to negative 2 pi, sine of negative 2 pi is 0. So what you notice is that the sine wave that we graphed on the right side of the y-axis matches the graph that we generated on the left side of the y-axis. So this wave repeats across the entire domain. So again, we have a small snapshot of the graph here, but the actual domain of sine of x is negative infinity to infinity. But do notice we have a minimum y value of -1 and a maximum y value of 1. So we could say the range of sine is -1 to 1. Using a similar technique of plotting points, we can examine the graph of the basic cosine function, y equals cosine of x. Once again, I want to point out the importance of understanding the cosine function. The input or the argument of the cosine function is an angle, and in the case of graphing, we're looking at the angle in radians. The output is a ratio that we obtain from the unit circle. So notice here we have variable y equals cosine of x. The input to that function x represents an angle, which we're stretching out on the linear x-axis. The output to that function, y, represents a ratio that we obtain from the unit circle. So recall that when we first defined cosine of an angle, we defined it as x over r. For the unit circle, where specifically we have r equal to 1, cosine of that angle is the x-coordinate from the unit circle. This x is different from this x. In the definition of our trig functions, cosine of an angle is equal to the x-coordinate that I obtain from the unit circle. So that's simply the definition of cosine. But in the function that we are attempting to graph here, we're going to allow x to represent the angle. Y represents the output of that function. That is, y is going to be the x-coordinate from the unit circle. So pay attention to the context in which you're looking at these functions, and be sure you know what the input and output represent. So let's work our way around the unit circle, making stops at the quadrantal angles to determine the value of cosine for each angle. So if we start with 0 radians, cosine of 0 radians is equal to 1. Notice we're picking up the x-coordinate there according to the definition of cosine. At pi over 2 radians, cosine of pi over 2 is equal to the x-coordinate, which is 0. As we rotate to pi radians, cosine of pi radians is -1. Cosine of 3 pi over 2 is equal to 0. And cosine of 2 pi back again to 1. So as we did with sine, we have a list of 5 ordered pairs that we can plot on the graph. Now, as I did before, I'm going to use a scale of 2 tick marks representing 1 unit on my graph, just to make it clear and easy to read. So let's plot these points. The first ordered pair is 0, 1. Then we have pi over 2, 0. Pi, -1, 3 pi over 2, 0, and 2 pi, 1. With these representative points, we can connect the dots for cosine, and instead of having a roller coaster shape like we did with sine, we get a bowl shape for cosine. Now, the graph will continue beyond the points that we have graphed here. So to find the points on the left side of the graph, or the negative angles, we're going to work our way around the unit circle in the negative direction. So if we rotate to negative pi over 2, negative pi over 2 has a cosine of 0. So we have ordered pair negative pi over 2, 0. If we rotate to negative pi, cosine of negative pi is -1. So we have ordered pair pi, -1. Rotating to negative 3 pi over 2, cosine of -3 pi over 2 is 0. So we have ordered pair -3 pi over 2, 0. And then finally, cosine of -2 pi is equal to 1. So we have ordered pair -2 pi, 1. So again, we see this repeating pattern like we did with sine. We also need to observe that this graph continues beyond where we've stopped it, and the graph will actually cover the entire x-axis. So the domain is -infinity to infinity. Like sine, the range of cosine is -1 to 1. Notice that the graph of both sine and cosine generates a wave. Because they are both waves, these are both classified as sinusoids. If you notice, cosine resembles sine. It's just been shifted on the x-axis just a little bit. For example, if we want to look at these graphs with our calculator, the most important thing to remember when you're graphing on a calculator is that to make sure that your mode is radian mode so that your graphs will come out correctly. So if I go to y equals, I can graph sine of x, and I can also graph cosine of x. Notice that sine is graphed here in blue, cosine is graphed in red. So they resemble each other. Again, the cosine wave is simply the sine wave shifted just a little bit. As you learn to graph trigonometric functions, your graphing calculator will be extremely useful to you. And so I do want to point out one option you have under your zoom button. If you choose zoom number 7, zoom trig, then the scale on the x-axis will be set at pi/2 units, which resembles the scale that we were using on our graph by hand. We do have a scale of pi/4 units here. Half of pi/2 is pi/4. But again, you can see those quadrantal stops on our graph by hand. Another thing that these two graphs have in common is that basic shape, whether it be the bowl shape or the roller coaster shape, is repeated across the entire domain. So both sine and cosine have an important property that we need to recognize. Let's examine this definition. If y equals f of x is a function and a is a non-zero constant, such that f of x equals f of x plus a for every x in the domain of f, then f is called a periodic function. The smallest positive constant, a, is the period of the function. So recall from college algebra that if you add or subtract a constant to the argument of an elementary function, then the resulting graph will resemble the parent function. It will just be shifted either to the left or to the right by a units depending on the sign of a. So this equation right here is saying that the y value of the parent function is equal to the y value of the shifted function. That is, we have a repeating pattern. For example, the y value here at negative pi is equal to the y value here at pi, and those points correspond to each other in that repeating pattern. So both sine and cosine are periodic functions, and the period is 2 pi. That is, over an interval from x equals 0 to x equals 2 pi, we see a snapshot of the shape that repeats across the entire domain. This is also true for sine. From x equals 0 to x equals 2 pi, we see a snapshot of the graph or the pattern that repeats across the entire domain. So the period of both sine and cosine is equal to 2 pi. The graph of the sinusoid, either sine or cosine, over that interval from 0 to 2 pi is called the fundamental cycle. The fundamental cycle. Let's look just a little more closely at the fundamental cycle of both sine and cosine so we have a good understanding of the pattern of these two graphs. Once again, I like to refer to the sine wave, or the fundamental cycle there, as the roller coaster shape. It starts on the x-axis, hits a maximum point, crosses the x-axis, hits a minimum point, and returns back to the x-axis. For the cosine wave, I like to refer to this as a bowl shape. So the pattern that we see repeating across its entire domain is this bowl shape. Considering the sine wave, it starts on the x-axis, it ends on the x-axis, and it crosses the x-axis at the midpoint between the beginning point and the end point of the graph of the fundamental cycle. Also notice it reaches a maximum point halfway between the first and second x-intercepts. Similarly, it reaches a minimum point halfway between the middle and last x-intercept. So the 3 x-intercepts, in addition to the maximum point and the minimum point, are called the 5 key points for the sine wave. The cosine wave starts up at its maximum point. It crosses the x-axis twice, hitting the minimum in the center, and it ends again at another maximum point. Notice the minimum point is the midpoint between the two original maximums. Also, the x-intercept is halfway between either the max and min or the min and max. So the maximums, the minimum, and the two x-intercepts are the 5 key points for cosine. These will be important to keep in mind as we learn transformations of our trigonometric functions.